in this video, we are going to see the del operator representation for the physical interpretation of expansion or contraction, which is further called as positive or negative divergence. So let us have a look. So the term is divergence. So for understanding the divergence, let us take the example of a balloon. The balloon is having this kind of shape. So now if we add some more air to the balloon, so that time the size of the balloon increases. So this is actually expansion. What we say, volume has been increased. Now whereas if we allow the air from this balloon to pass out, so the size of the balloon will decrease. So in that case we will draw a small balloon. So this case is called as expansion and this case is called as contraction. Now the expansion and contraction concepts using the del operator is nothing but the divergence. Here the divergence is the vector operation which is affecting on the net volume. Because of this divergence operation, we can say the increase in volume, the output is positive, we say positive divergence, and if the volume is decreased, that is contraction, we say it is negative divergence. So now let us have the representation of divergence and further talk about the divergence theorem. So as we know that the del operator has the form del del x ax cap, del del y ay cap, del del z az cap. Now if any vector A we take which has the form ax cap x component, capital Ay small ay cap which is y component, and capital Az small az cap which is z component. So for representation of divergence using the vector representation and the del operator, we can have dot product operation. So del bar dot of a bar. So here we take the dot product of both these brackets. So del del x ax cap, del del y ay cap, del del z az cap, dot product with ax cap, ay cap, az cap. So the dot product between these two brackets will give us del del x of capital Ax plus del del y of capital Ay plus del del z of capital Az. So here the divergence of A, which is represented by del bar dot of a bar, has this form, where we find the three terms, and in these three terms we don't find any unit vector. So I can say that the outcome of divergence is scalar in nature, whereas both the operands a bar and del bar, these are vectors. Now if it is the case that for any vector A the divergence is equal to 0, so let us have the representation. Divergence of a bar is equal to 0. So if we get to know the divergence of a bar is equal to 0, the physical interpretation meaning of this thing is that for the vector a bar there is no increase into the size volume, there is no decrease into the size volume, so it means there is no expansion or contraction. That is why the divergence is equal to 0. In any of the numerical problems you come to know that the value is positive, it means it is expansion. If the value is negative, it means it is contraction. Now let us have the effect of divergence in the three-dimensional space, so which is represented mathematically as, so mathematical representation of divergence of A in another form will be limit delta V tends to 0, delta V for the differential volume, surface integral A bar dot of ds upon delta V. So here delta V approaches to 0. Now if we take the contraction of any volume, finally the end will be in a point. For a point, we take into consideration that the volume is increasing. It will be in the form of geometrical shape sphere, we can say. So this was divergence. Now using the concept of divergence, there is a theorem called as divergence theorem. So let us have a look on divergence theorem. Divergence theorem. Now for divergence, we have discussed the example of a balloon which is going to increase in the size or decrease in the size. So like a balloon, if there is any object, let us say in the rectangular coordinate system, we take a parallelepiped or cube for analysis purpose. So here the divergence effect onto this particular object can be explained with the help of either surface values or surface area values or the volume values. So we can use two types of integrals, surface integrals and volume integrals. So the same physical concept we can have representation using two forms. One form is, let us say, closed surface integral A bar dot of ds bar, which is nothing but volume integral divergence of A bar dv. You can say that both these things are same. Why? Because surface integral is double integral. The two dimensions give us the surface integral. The volume integral is having three dimensions, triple integral. But here we take one differentiation. Del operator, the name is vector differential spatial operator or vector spatial differential operator. So finally there will be the two integrals on LHS as well as RHS. The physical procedure, whatever happen in expansion or contraction, here it is explained in the terms of surface integrals. The object is closed from all the sides. We have to take into consideration all the surfaces of that particular objects. That is why we put the close sign over the surface integral, and this is the volume integral of divergence of A bar. So this was divergence and divergence theorem. Thank you. In previous lecture, we have gone through the concepts of scalar, vector, scalar field and different coordinate systems. The coordinate systems have given us the positioning, locationing of a vector or the point into the three-dimensional space. Now, the topics like expansion, contraction, rotation of a vector. So for dealing with these topics, a new vector is now introduced here called as del. So let us see the new operator del and gradient. The vector operator del is represented by the symbol del, and a bar is given over the head of this del. So the long name of this operator is vector spatial differential operator. So as the nature of this operator is directional, we say it is vector. It deals with the space. If it is a rectangular coordinate system, x, y, z parameters. For cylindrical, rho, phi, z parameter. And for spherical coordinate system, r, theta and phi parameters are dealt by this operator. That is why it is also called as spatial. The representation uses different differentials directed to x, y, z, rho, phi, z or r, theta, phi. That is why vector spatial differential operator. In the rectangular coordinate system, the del operator is represented as del del x of ax cap, del del y of ay cap plus del del z az cap. Here, del del x, del del y, del del z are the differentials with respect to x, y and z directions. Whereas ax cap, ay cap, az cap gives the unit vectors with x, y, z axis. Now, using this vector spatial differential operator, we can have two types of operations: operations over scalars and operations over vectors. So operations over scalar is basically called as gradient, where the del operator is operated with any scalar value, let us say t. So the T can be any voltage, T can be simply temperature also. So operation of del vector over any scalar gives the resultant to be a vector, most of the times called as gradient. Now another type is operation over vector. So this operation has two more subtypes, where the operation performed with dot product and performed with cross product is there. They are further called as divergence and curl. So simply the representations are del bar dot operation with any vector A. This is supposed to be called as divergence. The operator is also vector. The A is also vector, the resultant is a scalar in the case of divergence. Whereas if you have cross product between the vector operator del and the vector A, so that time the outcome is also vector, which is called as curl. So now let us see more details of the gradient, curl and divergence further. So let us start with the gradient. Now to understand the concept of gradient, let us discuss one example. In this example, I take a metal rod which has uniform material configuration. So in the rectangular coordinate system, we represent the axes x, y and z, which are mutually perpendicular to each other and intersecting into the origin O. Now I have taken this metal rod which is parallel to y-axis. So we can have the measurement of length over this rod in terms of y1, y2 and so on. So the differential will be dy. Now beneath one of the end of this metal rod, I put a candle. So at this end, suppose a burning candle is put over here. So it is obvious that this end will be heated up. As the material configuration is uniform in the body of this metal rod, so the temperature at this end will be the maximum. So I can write T max here, and the temperature at this end where there is no candle, it will be the minimum temperature. I can say T minimum. So in the body of this metal rod, along the y-axis, we can say that there is a rate of change of temperature with respect to the length. So the length we can say in terms of y. So I can show the ratio of dt with dy. So it is the differential of temperature with respect to y. So with y the length changes. So the maximum rate of change of temperature we say called as temperature gradient. Here the temperature is a scalar quantity. As like we can have different scalar quantities like mass, like voltage. So in that case we can say voltage gradient into any circuit. Now the gradient representation in terms of del operator mathematically can be done like this. The del operator and the scalar t. There is no any dot or cross between the two operators. We know that the del operator is given by del del x ax cap, del del y ay cap, del del z az cap. So multiplying this del operator with t, we get del t by del x, ax cap, del t by del y, ay cap, del t by del z, az cap. In the example we discussed, the metal rod was aligned to y-axis only. That is why we discussed the differential with respect to the y parameter. But in general, the rate of change of any scalar quantity with respect to the space can have three components along x, y and z axis if we consider the rectangular coordinate system. That is why the three terms come into this picture. So these are the rate of change of the scalar quantities with respect to x, y and z. So that is gradient. Thank you. Hello friends. In the previous video, we have gone through the concept of del operator, gradient and divergence with divergence theorem. Now, the curl, which is one more operation taken with the help of del operator over a vector, which gives us the exact physical interpretation of rotation of a vector. So let us see the details of curl and further see the Stokes theorem. The term curl. So the curl mathematically represented as del bar cross of any vector a bar. The representation for divergence was having dot between the vector a and del operator. For gradient, there it was no dot or cross in between the scalar operator t and the del operator. So this was gradient, this was divergence and this is curl. Now to understand the exact meaning of curl, let us take one example. In this example, suppose this is a vector a bar. So it is pictorial representation of a bar having this much of length gives magnitude and this particular direction. So if this vector has some kind of rotation, so with this rotation, we know that for any vector, the field quantity is at the end point. So if it has counterclockwise rotation, it actually traces this particular area. Now you can see that if we have the integration over this particular counter, we say it will be a closed counter integration. So this integration will give us the idea how the vector a tip is having rotation into the three-dimensional space. Now see that while this vector a is having rotation, the vector a while having rotation will have a trace of area into any certain plane. Okay, so hence the curl of vector a can be written as del bar cross of a bar in terms of limit as it traces the area. Del s we say differential surface area, it will tends to 0 given by the closed line integral a bar dot of dl bar upon delta s. So it is actually the rotation of a vector with respect to the surface area, whereas the divergence was expansion or contraction of the volume and the gradient was maximum rate of change of any scalar quantity with respect to the space. Now the curl operation formula in terms of rectangular coordinate system we need to see. So let us have a look. We know that the del operator is of the form del del x ax cap del del y ay cap plus del del z az cap in the rectangular system. Now the vector a again has this form ax cap ay cap and az cap. Now if we have cross multiplication of these brackets of that of the del, and so this vector multiplication or the cross product we say we simplify with the help of this form. So the first row of this determinant will have ax cap, ay cap and az cap, the unit vectors along xyz. The partial differentials with respect to x, y and z belong to the second row, and the third row belongs to the coefficients of vector A along x, y and z axis. So this determinant, if we simplify further, it will give you the result curl of A bar will be equal to so this difference term will be associated with ax cap. This won't be plus, the second term has to be minus, and the third term will be having. So this is the mathematical formula for determination of curl. Now using the curl operation, one more theorem is put forward which is helpful for us to getting switch from line integral to surface integrals, which is called as Stoke's theorem. So let us have a look on Stoke's theorem. So in the case of curl, we have seen a vector A bar and its rotation keeping the starting point of the vector at center. Okay. So this was tracing a certain area. So the area can be represented by using the surface integrals, while the tip of vector A is making a circulation here. Okay. So this contour will be denoted by line integral. So here we equate the two, that is close contour integral or close line integral A bar dot of dl bar with surface integral, as the tip of vector A is having rotation, it will be del bar cross of A bar curl to ds bar. So here this is line integral, single integral, this is surface integral, means double integral. So we follow the same notations. Del bar t for a gradient, del bar cross of A bar for curl, del bar dot of A bar for divergence. Now if del bar dot of del bar t is equal to 0, okay, so it means gradient of t is 0. For example, we had taken the temperature to be the scalar quantity. So if del bar t is equal to 0, it means the temperature gradient is 0. So in the three-dimensional space region, whatever is considered for this particular example, in that particular region, there is no rate of change of scalar quantity with respect to the spatial parameters. So the scalar quantity, for example temperature, will be having the uniform or same value in the entire region. Now if del bar cross of A bar is equal to 0, it means curl of A bar is equal to 0. Curl is for the physical interpretation of rotation. It means the vector A does not have any characteristics to rotate into the three-dimensional space. So here rotation is absent, and in that case A bar is called as irrotational vector. Or if A bar is any field, so it is irrotational vector field. Now del bar dot of A bar, if it is equal to 0, it means divergence is equal to 0. So divergence is neither positive nor negative. So there won't be any increase into the volume, that is expansion, or decrease into the volume, that is contraction. So it means volume is fixed. There is no change into the volume. So A bar in such case is called as solenoidal field. Now along with this, we discuss certain vector identities which will be helpful in solving certain numericals or analyzing further derivations. So let us have a look on some vector identities. The first vector identity I have, that is del bar cross of del bar t, this is equal to 0. Now if you see the left hand side of this identity, del bar t, this is gradient of t. So here curl of gradient of a scalar quantity t. Now the gradient of t is measured along a linear direction. Maximum rate of change of any scalar quantity, for example temperature or voltage, along x, y, z axis or any arbitrary direction. Okay, so it is along a line, so it does not have any property of rotation. So hence curl of gradient of t will always be equal to 0. Now second identity representation is del bar dot of del bar cross of a bar. So if you have a look, del bar cross of a bar is a curl, and del bar dot of this particular bracket we shall pronounce divergence of curl of a bar. So curl is the representation of rotation, whereas divergence is the representation of expansion or contraction. While A is representing any rotation property, it does not affect the volume of this three-dimensional space. It does not increase any volume or decrease that particular value. So for that case, the divergence of curl of vector A is always equal to 0. So similarly, considering such facts, we have del bar cross of A. We know the formula for cross product. It will be given by del bar in bracket del bar dot of a bar minus del square A, and the last vector identity del square A is given by, so here the introduction of del square, sometimes the bar may be given or bar may not be given. We know that the del operator in rectangular coordinates has this form. So it is first order differential operator. When the del bar dot of del bar is taken, that time we get this operator del square, which is called as Laplacian operator, and by taking the dot product the unit vectors will be removed from it. So del square gives us a scalar operator. It is second order differential operator. So these were all the details related to the vector special differential operator del and its operation as gradient, curl, divergence, along with divergence theorem, Stokes theorem, and these vector identities. Thank you.